First of all, I want to tell you all of you guys sorry for yesterday's disturbance caused due to me. Actually, we cannot expect like that. So let's continue today's session. So I'm just about to share my screen. Yes, is my screen visible to all of you?
Yes, sir. Yes, sir.
Okay, fine. Thank you. In the last class, we have seen up to modeling and giving the inputs what we are about to design a rigid frame. Okay, so how to optimize and what are the things we have missed in that session, we'll see now. Actually, in case if you remember, I told you that there are different caged, nothing but effective length factors for different types of members. Okay, so these are 1, 2, and 3, 4. 1, 2, and 3, 4 are main columns. Means these columns include rigid frame action. That is why they have fixed at the top, and we have considered pinned bottom, or we have assumed pinned bottom at the base. Okay, that's why we have taken kz value 2 for these columns. Okay, let's take member 3 and 4. Okay, so now if you observe member 5, I have not divided member 5 into parts. If you observe these columns, we have divided into parts. That's why we have given unsupported length values for member 1, 3, and 2, 4. Why we have given like this for column? Okay, just in the last example, we have seen there is block wall up to 2.4 meter height. Okay, so there will be 2.4 meter in our example. I'm taking an example to explain you. So, okay, there is block wall up to 2.4 meter height and above is sheeted. Okay, so I have segmented the column into two parts, and first part will be at 3.4 meter height from the bottom. Okay, so this 2.4 block wall will come under member 2 and 4. Okay, that's why block wall will stop here. Actually, it will not prolong up to member 1 or member 3, right? So that is why I have taken 2.4 for member 2 and 4, whereas over that there will be sheeting, right? So what is the gut spacing? Actually here we have considered maximum of 1.5. Okay, you can take 1.5 for LY, UNT, and UNB as last discussed, right? Why we have taken LY, UNT, UNB? Do you guys remember, or again should I tell you how I have taken LY, UNT, UNB values, unsupported length values?
Yes, sir. Because of flange bracings and purlins.
Yep. If you take rafters, there will be purlins running over the rafter. Okay, so there will be continuous support where the purlin will be located at the top of the rafter. So if for example, if we take rafter, so purlins will run over the rafter, right? So that is why actually leave LY and UNB aside. First, UNT, unsupported length of top flange. Okay, UNT means unsupported length of top flange. It is 1.5 because the purlins will run for every 1.5 meter spacing. That is why we have considered 1.5 for UNT. Then you will get doubt what is LY and UNB. LY is unsupported length for minor axis. UNB is unsupported length for bottom flange. LY you can take it as for web. Okay, so How 1.5 meter will be transferred to the web? Actually, purlins will run over the rafter. So we can take UNT directly. But how this 1.5 we have taken for web and bottom flange also? Actually, we will provide flange bracings for rafter from every purlin. Okay, I have discussed this in the last class. Nothing but there will be a channel. Flange brace means a channel or a plate, okay, a thin plate. That is a flange brace that will be provided from every purlin to the rafter, like diagonally, if you see. Just I'll draw here so that you will understand. So, okay, if I take section at here, okay, if I take section at here, so this is the rafter, right? So over the rafter, purlins will run longitudinally. So I am cutting section here. So that is why purlins will run like this, right? So this is the bottom flange of the purlin. This is the top flange of the purlin, like this, right? This is the web. Okay. So purlin will run top of the rafter. That is why UNT will come, because it will be connected with the screws. Okay. But there will be a flange brace. Okay, like this, a flange brace will be connected from purlin to the rafter. That is why we have taken LY 1.5 for rafter and UNB also 1.5 for web. That is how we have taken UNT, LY and UNB values for rafter. The same concept will be applicable for column also. But why I have given 2.4 for members 2 and 4? Actually, there will be a block wall up to 2.4 meter height. Okay, if you observe in our example we have taken, there will be 2.4 meter block wall and above is sheeting. So okay, this 2.4 meter portion will come in the segment 2 only, and here in the segment 4 only. That is why but gut will come over the block wall, right? Gut will come over the block wall. So suppose let us take gut spacing is 1.5 and block wall is 2.4. Block wall will not provide any support to the column. It will just lean onto the column. It will take support from the column, but it will not provide any support to the column. Clear? So that is why this is 2.4 and gut spacing is 1.5. Which one is more? Which one is critical? 2.4 is the critical. That is why we have taken 2.4 for column 2 and 4. Okay. Over that there will be sheeting, right? So there will be guts like this. So that is why I have taken gut spacing for member 1 and 3 as LY, UNT and UNB. Is it clear to all of you?
Yes, sir, clear.
Clear. Okay. But leave that one. Now we are discussing about this column. Okay. This column, we are discussing about this column. If you take this column, there will be no guts, nothing is there. That means LY and UNT and UNB, all the unsupported lengths will be for full height of the column. But if you observe, we have not divided this column into segments. We have taken only one segment here. Okay, if you want, you can divide. But in our case, we have not divided this column into number of segments. So if you do not give LY, UNT and UNB also, there will be no problem, because we have not divided this into number of parts. By default, STAT will take member length as the unsupported length of the column. This is by default. If you do not specify LY, UNT and UNB, it will take length of the member as UNT, LY and UNB as unsupported length of the column. Clear? That is why we have not considered any LY, UNT and UNB of this column for this column. But what is the KZ value we have considered? I'm going to the editor here. Okay. KZ value we have considered actually 1. That is also I have not given, because 1 means 1 into anything, the same value will come. That is why I have not given it. If you give also, there will be no problem. Okay. 1, how it will come 1? Actually, if you go to some I'll open that one.
Buckling table, I think.
Yes, I'm opening that one. Do you guys remember table number? C.17, something will be like that. Okay.
എനിക്ക് ആകെ ഒരു സുഖമില്ല, അതാണ് ഒന്നാമത്തെ. ഞാനപ്പോ അത് ഇരുന്നിട്ടേ ഞാനിപ്പോ അങ്ങ് ജസ്റ്റ് എത്തി, ഞാൻ നോക്കിയിട്ട് ഞാൻ നാളെ.
So I did not find here. Actually, I'll show you. I'll show you the table.
അല്ലല്ല, കാറ്റില്ല, അത് മറ്റേ KSBക്കാരെ
Just Anil Kumar, please mute yourself while you're talking with others. If you have any doubts, you can ask me. Okay. Okay, guys.
Recording in progress.
Slide here.
Sir, in pick table number has shown, so you can find directly through.
Yes. I got it. Okay, so this is the table number CA71 in AAC 710 if you find. Okay, so these are the general values we consider. So if you observe here, what is the KZ value we have considered? Actually, we have not considered anything. That means KZ value, it has taken as 1, right? So what is the value of 1 here? Sorry, if you remember here, we are considering pinned base. So the top should be pinned here, right? Because we are considering pinned base, we are taking effective length factor as 1. So what is the top of the column? What is the support at the top of the column? That should be pinned, right? So in our case, we need to do the top of the column as pinned connection. How we can do that in our STAD? Just give me a minute, guys. I'm getting disturbance from someone. Okay, clear. Okay, so how we can release member 5 at the top? So there is one command. Actually, I think just 2 class before we have seen how to release members. Okay. Now I'm telling you in the start editor how to do that. Okay. So after the constant section, we have a command with name member releases. Okay. If you just type your name, you can see here member releases. Member releases. Which member I have to release? That is member 5. Okay, member 5. At what point you have to release? If you just hover the cursor here, it is showing green color at the top, blue color at the bottom. Or otherwise, if you click Shift E, it will show the start and end points of a beam. Okay, so at what point we have to release the member? That is at the top. That is, you are seeing green color. 5 for 5 member, you are seeing green color, right? So that is 5 start. Green color means start, blue color means end. You can see that by clicking Shift plus E. Okay, so 5 start. Which one I have to release? Movement along Z direction, because I'm doing plane. If you see here, I'm doing plane structure only, 2D structure only. So in 2D structure, movement will be developed like this. So the axis of rotation of movement will be MZ, Z axis, right? That is why I have to release the movement so that it will get pinned. That is why I am releasing MZ. 5 start MZ. Is this clear to all of you?
Yes, sir, clear.
Okay. Member releases is the command. Yes, tell me.
Sir, I have doubt. This number M is that means now every structure on X direction only, na? How to reduce Z direction?
Oh, so you will get doubt this for sure. I will show you after analysis why I have taken MZ.
Okay.
Okay. I will do analysis. After that, I'll clear doubt. I'll clear your doubt. Okay.
Okay.
Okay. So just I'll close it for you. I'll do the analysis. Oh shit. Mainly this is the problem with cracked versions. We'll get some errors doing this thing. Okay, so this is okay. We have released MZ here. Okay, so that is why you are seeing some round type symbol you are seeing here at the top. That means we have released. Okay, just I'm analyzing the structure by clicking Control 5. Okay, Control F5. Sorry, Control F5. If you click Control F5, you'll be able to analyze the structure. That is run analysis command. Otherwise, there is one option here. You can see here, run analysis command. Okay. Analysis and design. This is the run analysis command is there. You can click by doing this, or otherwise you can click Control F5. Okay. So after the analysis completed, just I'm going to the post processing mode to check MZ values here. Okay. So I'm doing MZ values. I'm taking it for dead load, for gravity load. I'm taking. If you see here, we have released the moment. That is why moment is not coming onto this column. MZ means actually we will calculate bending moment, etc. for every member, right? For example, while calculating manually also, for example, we have taken a simply supported beam with something, any loading. Okay, we are calculating bending moment diagram. Okay, so if you calculate bending moment diagram, what is the rotational axis for that moment? So it is moment is coming like that, right? Moment is coming like that. So if you observe, what I can say, if you observe the how the moment will be applied, I'll draw here so that you'll understand. This is how moment is coming on the rafter at this point, right?
MZ direction.
Just a minute. Someone does not know how we have taken MZ. Okay. This is the moment coming onto the rafter at this point, right? Will you agree with me?
Yes, sir.
Yes, right. So what is the axis of rotation for this moment? Axis of rotation means if the axis has to pass perpendicular to this moment. Okay, here it is in the xy plane. So perpendicular to xy plane, what is the axis will be there? That is z axis, right? So that is why this moment will be called as mz. Someone asked about why we have taken mz. Is it clear now?
Clear, sir. I'm not asking why you're taking MZ. I'm asking this plane is only x direction only, no, x and y direction only.
Okay, plane is x direction, y direction. Okay, there is sorry, this structure is in x and y direction only, but
Yes, sir.
the moment coming is mz. This is notation, just a notation. Okay, this is just a name. Okay,
Okay.
this is just like a name or notation, I can say. Clear?
Okay. Yes.
Okay, fine. So I'm going to the analytical model again for this. So, okay. So we have given some properties and we have given some releases here. Okay. There is nothing there. If you want to fix this also, you can fix. Nothing is there. Okay. You guys can fix the column here. No problem at all. Okay. You can fix the column, but KZ value will be deferred. KZ you have to give. What is the value of KZ you have to give? That
Two,
is
sir.
2. Okay, if
Sir,
you observe here, yes, tell me.
One question, sir, here. Sorry to disturb.
Uh,
Sir, in what cases will fix the
yes,
column?
that is the very good question, actually. So if you observe here, just I will show you an example in this only. Just I'm going to the post processing mode. Okay, just I'm checking the displacement of the node here. So okay, if you observe what is the maximum displacement here, you can observe displacement means x direction. So okay, what is the horizontal displacement of this node? I can say sway. What is the here maximum 50 around, right? Just for your understanding, I'm fixing this now. Fixing means I have to remove the release command here, right? I'm commenting this section just by clicking by clicking Control K. Okay, Control K will comment, or otherwise you can right click here. Comment, uncomment is here. Comment means whatever the line we are giving under comment section, that will not run in the analysis. Okay, so that is why I'm fixing here. Fixing means I have to release the I have to remove the release command, and I am changing this KZ value into 2. KZ 2 for member 5. So what will happen? We'll see here. Just I'm going to the post processing section again. So okay, just displacement. Okay, okay. If you click this node, what is the maximum displacement you have observed here? Okay, if you click this node, what is the maximum x displacement you have observed here?
20.
20.
Yes. What we have observed previously?
40 mm.
Yes. What is the difference between these two?
20 mm reduced.
Sway controlled. Main point is sway controlled here. Okay. we can control the sway by using fixing. Okay. And there is one disadvantage. If you click, if you fix here, there is one disadvantage. What is the disadvantage? Okay. If you see the unity check ratio here, 1.68, this column has failed in buckling because we have increased the effective length factor for buckling, right? So obviously length of buckling length of the column has been increased by fixing at the top. Do you got my point? Buckling length of the column will be
Yes, sir.
increased by fixing at the top because we have given KZ as 2. Actually, what is the length of this column? 9.2 something. But you are giving KZ 2 by fixing at the top. So what is the effective length of the column now? It will be around 18.4. So that is why this column is failing here. Okay. In previous case, if I have released here, Control Shift K, that is uncommented here, these lines, and I'm changing this to KZ1. Okay. So now let's see the analysis result. So, okay. Analysis results can be seen by right clicking here, structure diagrams, design results, show diagram. Clear? So if you observe here, what we have observed there, 1.68, the ratio has been reduced to 1.55. Okay, that is how we can reduce the section here. Okay, though there is no much difference in the ratio because this length is more. Actually, 9 meters is more. 9 meters means if you observe practically, it is of 3 floors height, approximately, right? So the column length is that much unsupported. That is why it is failing in buckling anyway. Actually, the ratio can be reduced if we release here. Okay. That is how it works. Okay. Now let's see how we can optimize.
Question, sir.
Yes, tell me. Sorry.
We do check. When we do check sway, we do check sway or deflection of column.
What do you think the difference between sway and deflection of the column?
I want to ask the same question, sir. Please.
No, actually, sway of the column, deflection is the same actually. Okay.
Yeah.
The horizontal deflection is technically termed as sway. Okay. In some cases, we can say it as drift. Yes, tell me.
Yes, sir. Go ahead, please.
Right. So now we will check for optimization, how we can do optimize here. Okay. So what is the best way of doing optimizing? Okay. In general way, if you see this syntax, first one is starting web depth, next one is thickness of the web, the next one is second depth of the web. This is top flange thickness, top flange width, top flange thickness, bottom flange width, bottom flange thickness. So I think this syntax is clear. I have explained this one in the last session. So this syntax is clear, right? So how to do optimization? So if you increase the thickness of any member, the weight will increase. Okay, that is why we have to pass the member with by changing the depths only in the maximum extent. Okay, so by providing depths only, we have to try to pass the section. Okay, in the case if it is not passing, then only we have to go for increasing the thickness. Okay, if you observe here, I'm doing optimization for this session, for this section. Suppose I'm taking member 1. Okay, if I double click member 1, if you go to steel design, what is the critical value it is showing? If you see, there is something, I'll tell you, I'll show you these sections, these clauses, everything. Okay, just in this session, just please remember that equation H1 1B is for this section is passing critically in combined flexure, combined moment and shear. Okay, both is acting simultaneously, nothing but web is also governing here, flange is also governing here. That is telling this equation H1 1B. Okay, is there anything? Okay, all the members are critical H1 1B only. Yes, yeah. If you observe this section, if you observe the member 7, it is critical in section G1. Section G1 refers to the shear only. Okay, so shear only here, the critical factor, nothing but you can reduce the flange dimensions. Okay, you should not touch the shear value, nothing but web thickness. Shear, nothing but web thickness. Okay, you should not change the web thickness provided over here. What is the web thickness here? 6 mm we have provided. That is the critical one here it is taking. Nothing but still the value is 0.422. I have told you in the last class, if you get the value around the 1, it will be economical. But here it is 0.422. The section is critical in section G1. Section G1 refers to the shear only. Shear only, nothing but you can reduce the flange dimensions, right? You should not touch the web thickness. That is how we will see. And if you double click the member 5 here, what is the critical here? H1 1A. So this column is failing in H1 1A. H1 1A is buckling. Okay, this column is fails in buckling. H1 1A refers to the fails in buckling. H1 1B refers to the combined flexure and shear, and section G1 refers to the shear only. These three are the main conditions we will see in the PEB structure, or I can say steel structure here. Any doubt here? I'll show you these sections, how they have taken like this. Okay, I will show you. As of now, do you guys any doubts here? Just you can share your opinion. If you guys do not understand, I'll explain again. H1 1B refers to the combined flexure and shear. G refers to the shear only. H1 1A refers to the buckling. Okay, so H1 1B, you should you have to increase the depth of the web or increase the thickness of the flanges. Okay, clear? And if you see this is critical in G1. G1 means web thickness you should not touch. Okay, whatever the points we can consider here, you can reduce the flange dimensions and web dimensions also you can reduce, but web thickness you should not reduce because it is critical in web thickness only. And if you click critical, member 5, it is critical in buckling. Buckling means you have to increase the flange width. Okay, here you have to increase the flange width. Here you have to increase the thickness if it is failing. Right? Clear?
So say it again, sir.
Okay, fine. Just I'll open a notepad to explain you this. Okay, so I'm taking member 1. Okay, so if you double click member 1, go to the steel design. This
Okay.
member is critical in H1-1B. Yes, anyone is saying something?
No, sir.
Sorry?
No, sir.
No, clear. Okay. So this member 1 is critical in H1-1B. H1-1B increase indicates, sorry, H1-1B indicates combined flexure and shear. Okay. Whereas the other thing we have seen is, if you double click here, if you go to the steel design, this is what is the critical here, G1. Okay, G1, G1, where is the notepad? G1 indicates critical in shear. And if you double click here, go to the steel design, it is failing in H1-1A. What does this H1-1A refers? Okay, H1-1A refers. These are the simple terms I'm telling you. If you do not understand anything, just let me know. Critical in buckling. These three are clear?
Clear, sir.
Yes. Now, what you have to do for this combined flexure and shear, you have to increase the depth of web or thickness of flange. Thickness of flange. Okay. In the next one, if it is fails in shear, you have to increase the thickness of web. Clear? If it is fails in buckling, you need to increase the flange width. Okay. Now this is clear. Just okay.
Yes,
In the for the first time, it is somewhat confusing. Okay, by doing the practice, you'll get handy all these points. It is clear now. Okay.
Yes, sir.
By taking reference from these points only, I am doing optimization. Okay. If you observe here, H1-1B refers to increase the depth of the web or thickness of flange. Just now I told you, increasing the thicknesses will tend to increase the weight. Okay, increase in thicknesses anywhere, that is flange or web. If you increase the thickness, that is tend to gain more weight. Instead of that, you have to try to pass the section by increasing the web depth only. Okay. Okay, anyway, the member 1 is passed here, so it is around 1. So if you observe here, what is the ratio here? 0.964. Okay, 0.964 is near to 1, so no need to bother about this member. If you go to member 2, that is the ratio here is the ratio here is 0.815. What is the critical here? H1-1B is critical here. Nothing but you cannot decrease the depth or decrease the thicknesses. Okay, instead of that, you can try to reduce the thickness of web here. Here also you can reduce the thickness because it is critical in combined flexure and shear. It is not only in the shear. So I'll try to reduce the shear only. Okay, because if you decrease the thickness, it may get failed here. So this causes more weight. That is why I have reduced it from 8 to 6. Okay, so just keep it like that. And if you go to member 5, so it is failing in buckling. What is the point I have told you? If the system fails in buckling, you have to increase the flange width. So how this will work, we will see. Previously I have given 200. Now I will try to give 250. Okay, 250 by 10, something like that. Okay, just let me check with the result. Okay, keep it done, keep it aside. And then member 6, that is in the rafter only. Okay, so here it is, the ratio is 0.736. Okay, the key point I want to tell you is that since the span is more here, okay, here 27.15. okay, generally if the module is more than 20 meters, I'm telling you practically this point, if the module means two clear span between two columns. Okay, if the module is more than 20 meters, dead load will govern more than wind load. Okay, dead load, I can say gravity loads will govern more than wind load. Actually, if I draw a BMD here, where is that? Okay, yeah. Right, approximate gravity load BMD will be like this, right? So you have to increase the thickness at the bottom, you can decrease the thickness at the top, because this has to counteract, actually coming BMD is like this. Okay, so if the rafter has to counteract this BMD, it has to be strong at the bottom, you can reduce at the top. That is the key point you can do here. That is why I'm just doing that thing. Okay, I'm reducing the top thickness here. Okay, bottom thickness I'm not reducing. So here you have to do one thing. 10 plus 8 is 18. Here web depth is 800 only, and the remaining 20 is coming from flanges. Actually now it is becoming 18. Is my explanation is understandable to you? Are you guys feeling any boring here? Or not understandable?
Little difficult to understand.
Huh?
I think it's okay. Everything is okay. Little difficult to understand what is making
okay.
changes.
Technically, yes. This is, since I'm going much more technically deeper, you guys feeling like that? Yeah, true.
Yes, sir. Little.
So
No problem. You can go with sir. Any doubt we will ask.
Okay, fine. Thank you for your support. Just for this point only, I'm going to the post-processing mode here. I'm clicking NZ by taking the dead load here. This is the point I'm telling you. Okay, the BMD is like this, right? To counteract the BMD, the entire system should not fail against movement. To counteract this BMD, you have to increase the thickness at the bottom. To counteract this, I'm again telling you, to counteract this movement, you have to increase the thickness at the bottom. You can reduce the thickness at the top. Okay. Again, one point, one doubt will come to you. Sir, can we change the thicknesses of the flanges from top to bottom? Yes. In PEB, it is acceptable. In PEB, it is acceptable to change the thicknesses of flanges from top to bottom. Okay. Okay, I'm reducing the thickness at the top here. If you observe 7 also, you can follow the same. Okay, meanwhile,
Sir, one doubt, sir.
yes, tell me.
You told me, tell me now, if you the PEP structure, it is acceptable to change the plant's thickness.
Yes, yes,
Right,
yes,
sir.
yes.
But where is not acceptable, sir?
Huh?
If you not acceptable, where is which structure is not acceptable to change the plant's?
Generally, in PEB structure, it is acceptable. Okay,
Ah.
but no clients ask you it is not acceptable. But till now, I did not find any case like that.
Any other structure is there? I am asking any other structure. It is not acceptable to change
Any
that
other
plant,
structure, it is not acceptable means if you go to conventional steel, okay, conventional steel is nothing but you have to go with hot rolled members only. All these we are doing here are welded plates, okay, welded plate I sections. Yes. If you go to the conventional steel structures, those are made up with hot rolled sections only. Hot rolled sections are the sections with same dimensions at top and bottom.
Yes, yes.
Right. In that case only we cannot change. If you are going for PEB, you can change. Clear?
Okay. Please.
Yeah, thank you. Just I'm doing for 8. Actually, 7 for 7 member, you are seeing the ratio of 0.422. Okay, 0.422 means that is much lesser than 1. So nothing but you can reduce the section heavily. So don't reduce the depth, because why I'm not advising to reduce the depth, because this module is 27.15. This section, if you reduce the web depth, it may get failed in deflection. It may pass in moment and other factors, moment and shear and buckling, it will pass. But if you see the serviceability condition, the deflection, in the deflection, it will get failed if you reduce the web depth. That is why I'm not advising to reduce the depth here. Instead of that, I'm reducing the thicknesses only, because the thicknesses anyway tend to gain more weight. So I'm reducing the thicknesses. Okay. In this portion also, this value is for 8. If you see here, I'm zooming in, 0.566 utilization ratio. So you can also reduce for this. Okay. But the key point here is the flange thickness should not be less than web thickness in any case. Okay, so here you cannot give 5 because minimum thickness is 6 here. Web thickness is 6 here. That is why you have to maintain minimum 6 or more. Okay, and this is also I'm taking 6. Okay, if it is failing, then we can increase. Okay, 9 is around 0.783. So it is coming just closer to the 1. Okay, just I'm what is the critical part here? The bending moment is at the bottom. So top part will be critical here. So top part I don't want to reduce here. Just bottom thickness I'm reducing. 10 also I'm doing like that. 11 also the same. 12. In the 12, the bending moment is changing. Contraflexure. So you can change all the thicknesses here, no problem at all. And if you observe 13, the bending moment is top. To counter the bending moment, the section at the bottom should be strong. So you can reduce the top here. You can reduce it to 8. And if you observe, yes, this is the critical one. If you observe this one, double click here, steel design, it is failing in H1 1B. Nothing but already we have increased the depth to maximum extent. Okay, this is 920 is almost 1 meter. Okay, 1 meter depth beam, that is much more deeper. Yes, so If you feel like that, you can increase the thickness here. Okay, you can increase the thickness here because bending moment at the top, I'm increasing the thickness at the bottom. Okay, just clear. Here also you have to change all these things, round figures. Okay, 600 plus 6 plus 6, 612, 712, 612. Here also 612, 16. Why 16? 10 plus 6, 600 plus 10 plus 6, 16. Here also the same thing, 16. Here also the same thing, 16. Do you guys feel any? Oh, sorry, here I have not given bottom thickness. What is this thing? 12, huh? 12 bottom thickness also. I'm reducing it to 6. If you guys feel any complexity here, please let me know. I'm ready to explain you again. Yeah. The main concept here is you have to understand.
Sir, one doubt, sir, here.
Yeah, just tell me.
So, what is the like any web to flange thickness? Is there like any criteria? I mean, you are using a 6 mm web and 12 mm flange.
Yeah, yes. This I have discussed, I think, in the
Yes, sir. You discussed that, but I'm.
yes. In the practical way, what we are following, you are asking, huh?
Yes, sir. That is there.
Yes.
We have that ratio is there. Depth
Yeah.
by width.
Yes. I'll show you that thing. What I am following here, as per my company. Okay, don't feel anything. Okay, if you enter any company, they will provide you the steel properties. Okay, every company will have plate inventory. Okay, plate inventory means a certain thickness of plate will have certain flange width like that. Okay, what is the thickness of width to thickness ratio, depth to thickness ratio, web depth to flange width ratios, all these the company will provide you. What I have observed, I'll show you in the text itself as of now. Just I'm rounding it off. Just give me a minute. Okay, just I'm closing it. Okay. Before going to the analysis, someone asked about this, so I'm going to this. Okay, so this we can call it as plate inventory. Okay, so how the plate inventory? Okay, every company will provide you certain plate inventory. As I'm doing most of the projects according to the AISC, okay, there are certain limits for me. Okay, just first one is depth of web, dw by thickness of web, tw. Where is that? Yeah, tw should be less than or equal to 180. It is lender section actually. Okay, this is the value we are following. Okay, and the other thing, what is remaining here? Yeah, bf by tf. bf by tf 33 0.33. And what is the remaining dw bf tf? Yeah, dw by bf by 2bf. This is first one. Greater than or equal to 2. Just give me a minute, guys. Yeah. These three are the points we are following actually. In this example also, I'm following the same. Okay. Depth of web by thickness of web is less than 180. All these indicates, okay, American standards, because this design is based on AISC, right? The next design will be Indian standard. Okay. DW by TW will be less than or equal to 180. Width of flange by thickness of flange will should be less than or equal to 33.33. D by 2BF should be less than or equal to 2.5. Okay, if you observe anything, I'm just opening star data to check the values we have provided correct or not. Okay, so D by TW should be less than or equal to 180. Okay, suppose here I have provided 600 by 5. Okay, web is 600 by 5. So it is coming 120. It is less than 180. Okay, so anything, the minimum is 5 is here. 600, the minimum thickness is, I have provided 5 here. You can provide 4 also in ASC, because the web depth, web thickness minimum is 4. Okay, according to my company. Okay, but BF by TF, if you observe any BF is nothing but width of the flange. Okay, or you can say critical, this one 200 by 6. Okay, if you calculate 200 divided by 6, that is coming under 33.33. so this also, but in the rare cases you can follow this one. Okay, and D by 2BF, if you observe 600 divided by 2 into 200, that is coming under 1.5, so it is less than 2.5. This is the plate inventory I have followed here. Okay, don't bother about this plate inventory. They whatever the company you are working with, they will provide you at the start of your career. Okay, all these also, for example, what are the thickness of plates available for 125 mm plate, or 150 mm plate, or 175, or 200, 250, 300, anything. What is the thicknesses available for this plate? They will provide you according to the plate inventory only. You have to follow as per the company rules. Okay, so is it clear now?
Yes, sir. Yes, sir.
Yeah, all these things will be company internal matters only. Actually, I should not tell you all these things. All these are company internal matters only. That's why I have not disclosed up to this thing. Since you have asked me, that is why I have told you. Okay, actually I should not tell this. All these will be company internal matters only. The company will provide you anyway if you join in a company. Just I'm trying to do this one. Just I'm right clicking the structural diagrams, going to design results. If you click show diagram, you check unity ratio here. So okay, there are some members failed here. Okay, generally this blue color is also failure, and red color you have seen in the previous design. Okay, that is also failure. So you will get doubt what is the indication of red color and what is the indication of blue color. Blue color failure, nothing but if the failure indicates if the unity check ratio is in between 1 to 1.5, it will show you in blue color. This is start by default. You can also change. Okay, that is secondary matter. You can also change the colors as you wish. Okay, if by default the stat will provide you, if the unity check ratio is in between 1 to 1.5, it is in blue color. If it is more than 1.5, it will be in red color. Red color means much more failure than expected. Okay, blue color means it is okay, it is just failed, like that. Okay, that is the indication here actually. So just I'm going to again this one. Actually, what we have changed here, actually here the thickness is, we have provided 8 previously. I have reduced it to 6 mm. That is why it has failed. Again, I'm going to thickness 8. Okay, this is coming around 1, so I should not change this. Okay, if you see here,